So I grabbed this Southwest Technical Products 6809 base system last November, right around Thanksgiving time. It'd come up for sale on Facebook, and I wasn't quite sure what I would do with it at the time. But since they don't go up for sale that often, I figured I'd grab it. I'd grown up with a 6809 base system since my parents got me a TRS-80 color computer as a Christmas gift in 1982. I figured that I could possibly get Nitrous 9, OS 9, or at the very least Flex running on this system. So I started to do some research to see what I could find for these Southwest Technical Product systems. And I came across Bob Applegate's Corsham Tech site as I was looking for any type of modern day peripherals or things that would kind of extend the life of these systems. I picked up a couple prototype boards from Bob as well as some other ancillary boards that might help in troubleshooting or get this system running. I also looked on Facebook and eBay for any old boards that might be up for sale. And I happened to come across this Newtech Model 68 music board for sale on eBay. Unfortunately, I missed out on the auction, but the seller did an outstanding job posting both front and back images of the board where you could actually see all the component values and the traces. I figured with that information, I'd give it a shot to reverse engineer the board, even though I couldn't find much information on Newtech at the time. The board looked extremely simple, so I figured I'd give it a shot. As I got into it, I realized that the R2R ladder on the Newtech board very closely paralleled the 6-bit DAC used in the TRS-80 color computer. Having done some coding of the 6-bit DAC on the color computer, and most recently a collaboration effort with Simon Jonassen, and for those that don't know him, he's well known in the demo scene and also known affectionately as the madman in the Coco community because he simply does mad things with code. I had originally found a version of this 4-voice music player, which was based on an algorithm that a gentleman by the name of Hal Chamberlain had published back in, I think, September 1977 issue of Byte magazine. The 4-voice music player was the basis for about 95% of color computer games distributed throughout the 80s. So Simon and I took this algorithm and streamlined it. Simon did an incredible job of optimizing the code and even created a version that's an IRQ-based background player, which leaves about 50% CPU left over for other code execution, while I worked extensively on optimizing the note tables and creating individual wave envelopes for different harmonics and tone qualities of music playback. I also worked on a few utilities to create the waveforms and to make transcoding of music and the note data more efficient. So at this point, I figured I would take the code that Simon and I had worked with and modify it to work on the Southwest Technical Products 6809 system I had picked up to parallel the efforts of reverse engineering the Newtech board. So after creating a schematic and PC board layout in KiCad, I posted an image of the prototype I had designed over on the SS50 and SS30 Facebook group. Shortly after doing that, I discovered that while Bob over at Corsham Tech didn't offer music board through his site, he had created his own version of the Newtech music board and made it publicly available through GitHub. Coincidentally, a gentleman named Robin Grosset had found Bob's GitHub page and had some of these boards produced. Robin has a 6800 Southwest Technical Product system and did an outstanding job of creating a video which shows how he built the board and wrote some code to produce speech playback with his 6800 system. So after seeing that Bob had created a version of the board, I was at a bit of a crossroads. Instinctively, though, I had decided that I'd already invested quite a bit of time in my design and that there were enough differences between Bob's board and what I had planned to produce that I would press on. As I mentioned, in Robin's video, he did great work in producing speech. This video will show the current progress of my prototype and how to make these Newtech boards play music. Okay, so let's have a look at our prototype. And what I've got here is one of Bob Applegate's Corsham Tech SS30 bus prototype boards. And as you can see, we've only got a few lines coming off the SS30 bus. On the right-hand side, these 6 green lines are our upper 6 bits of our 8-bit data. So it's bits 2 through 7. The blue line is our clock signal. The green line is our read-write enable, and then the white line is our board select. So the clock, the read-write, and the board select actually get fed into this 74LS10, which is a triple 3-input NAND gate. Those all get combined into one signal that come over here to our flip-flop, which is 74LS174. And then this flip-flop, based on that clock signal, is latching in these 6 data bits and basically functioning as a buffer to hold those bits, which in turn get fed into this 4050, which is a non-inverting buffer. And what this is functioning as is a line conditioner to make sure that we've got strong 5 volts coming in to our R-to-R ladder here. One thing I did want to mention is you can see these lines crisscrossing. There was a bit of questioning on the forums, and I think Facebook as well, as to why Newtech decided to go that route, and I in turn decided to keep it that way. And the reason why is because the original Newtech board is a single-sided board where everything is just soldered on the underside, and the way to get the 6 data lines into the circuitry without having a bunch of jumpers over the top of the board was to have this layout. But it all works out because they get flipped here, and then in turn they get flipped on the backside coming out of this 4050 or into the 4050 and then out. So it all works out. But the 4050 feeds the strong 5 volt signals from each of the data lines into our R2R ladder here. Least significant bit on the right, most significant bit on the left. And with these 6 bits, we actually have a functioning and essential 64 step of digital analog converter. So this is basically just a really elaborate or non-elaborate, however you want to look at it, voltage divider that provides 64 different levels of voltage out to our LM380, which is our 2.5 watt audio amplifier. There's some supporting circuitry here, a low pass filter, a little bit of a volume control, and that gets passed out to our speaker. And I've just got a little PC monitor speaker here that I've been using. The only other line that we've got is this yellow line, which is our 8 volt line, which gets fed up into our op amp here, our 2.5 watt audio amp. On my system, it's closer to 10 volts, but it's 8 volts here. And then the only other thing that we've got that's not showing here on the board, I'm using the voltage regulator, that's the 5 volt voltage regulator that's on the prototype board. The finished product will actually have its own small TO92 like transistor form factor linear voltage regulator, which is 5 volts as well. So these chips down here are 5 volt. This one here is functioning as 8 volt. So that's basically it. Okay, so this is how I have the system set up. I've got the prototype board slotted in slot 3 of the Southwest Technical Products 6809 system, running the original 6809 processor board. I have some modifications behind there, though. I'm running one of Corsham Tech's, Bob's 64K boards. The 64K board that came with the system is perfectly okay, but I've just been playing around with some of his stuff, and this is a really nice board, so I've got that in there. The other board that I've got is his serial board. It's a USB serial board. The serial board that I had in mind that came with it, the 12 volt, the negative 12 volt voltage regulator was shot on it, and I have a new part. I just haven't done it yet. So this board does an outstanding job. So the board, again, is plugged into, the prototype board is plugged into slot 3. I have the oscilloscope hooked up to the output of the R-to-R ladder, the DAC there. And then I also have the speaker tucked up in the corner there. The other thing that I have is a line out, which is the audio output connected to stereo, so I can get amplification on it. Got the oscilloscope set up so I can look at wave patterns, and just my laptop set up where I can have the terminal to send files over to the serial line over to the system. And they're just basically S19 files. That's the only way that I have to transfer data into the system. Haven't gotten the disk drive system going with it yet. So that's the current setup. Okay, so what I've done here is I've inserted some LEDs into our R-to-R ladder. one LED for each bit that we have coming into the DAC. The reason why I've done this is just to illustrate how we can turn on each individual bit value in the ladder and to show you how the voltages change as we adjust the bits coming into the ladder. One thing I did want to mention is the LEDs are only here for visual purposes. I'm not going to leave those in there either for the prototype or for the final board. And the reason for that is twofold, because the LEDs and the resistors that are in circuit right now actually add to the voltage divider on this end of it. And as such, it decreases our output voltage to about 3.5 volts as opposed to 5 volts that we want coming into the DAC. So we're only at about 70% of our output. So that's going to affect the volume coming out of the ladder. The second reason why is because we're using 1% metal film mil-spec resistors for our ladder. And for the LEDs, I'm just using off the shelf 5% LED or resistors. And what happens is because they're only 5%, they can affect the tonal quality of the ladder. We want a really tight tolerance on the R ladder. So the other thing that you can see is all the LEDs are on right now. And if we examine our memory value that we have, we're using slot 3, so we can examine port E030, and we're at FC. And if you look on the oscilloscope, we're at like 3.5 volts output right now, maybe just a little bit shy of that. It's about 3.5. And so that's representative of all the LEDs being on. So what we can do is we can turn them all off by sending 00 to the port. And that turns off all the LEDs, and we see that the voltage drops down to 0 at that point. And what we can do now is show how we can turn each bit of the DAC on. And by, again, going to port E030. And remember, we're skipping over bits 1 and 2. So we're starting, or bits 0 and 1. So we're starting with bit 2. So to turn that on, we want to send a value of 04. And there's our first bit. So we can go right down the ladder and go to our bit 3. And as you can see, FC keeps coming back. And the reason why we're seeing FC is because the 6 data lines that we have coming into our op amp, or our flip-flop right down here, actually have a residual voltage coming off the pins, and it's enough to set those high. So when we do a read on that port, we're seeing those in turn as high. So that's why we're seeing FC there. But we can turn on bit 3, and it's just sending 08. And there's our second bit in the ladder. And we'll just go right down the line. And as you can see, so now we're up in our next nibble, our upper nibble. And you can see as I'm changing these values that our voltage is gradually stepping up on our oscilloscope. So next would be 20, goes up a little bit more. 40, oops, missed it. So let's start over. 40, and then we'll be at half voltage with 80. And there you go. So you can see how each bit, as we shift it into that memory location, increases the voltage going out of the ladder. And if we, again, want full voltage, what we can do is put our FC value out there, turning all bytes high. And there we go. Okay, so while I still have the LEDs plugged into the board, there's one other thing I wanted to show you, and that's what a music selection would look like as it's being sequenced through the music board and as the bits are going through the DAC. So to send a file over to the system, what we can do is we can hit send text binary file through the terminal. These are S19 files. We'll select this lemon selection because it's a good song to use because the notes are longer and you can actually see the bits being held longer as they sequence through the board. So it only takes a couple seconds to send over. It's a short song. Now to start the song, what we need to do is change where our program counter is. And to do that, we can just hit Control P. It's currently at F814, which is our SBug monitor. Our code starts at E00, so we can just put that into our program counter, verify that it's there, and then we can just hit G for go to resume. So there you go. It's kind of neat seeing the music being sequenced through the music board and the bits being shifted through the DAC. So now that we've taken a look at the hardware, let's take a look at the code to see how the 4-voice music player actually works. As I mentioned earlier, this was based on an original algorithm from Hal Chamberlain in Byte magazine, September 1977. And even though this code has been extensively rewritten, almost to the point that you can't even recognize it compared to the original version, I leave these citations in here just as references so people can see how this evolved over time. So the code itself is actually broken up into 4 primary sections, and what I'm going to do is I'm going to skip down to the bottom just to go over the note structure first, just so you can see as we have a reference as we're going through the actual algorithms. So the first thing I wanted to mention is the note data table, and these are the notes that are actually brought in from sheet music or other sources to be played back. And the structure of the note format is the first byte here is the note duration, and then the 4 sequential bytes after that, as you remember this is a 4-voice player, are the frequency for each one of those respective 4 voices. And these values here actually represent a value into our lookup table, which is our note table up above. And we currently have it set up, I think there's 63 notes here, and it's a full 5 octaves, so basically a 61 key piano basically represents that pretty well. So I think we go C2 up to D7 with this particular note table. So with that in mind, what we can do is we can go back up to our algorithm section. Oh, and one other thing, another section is the waveform table, and each one of these waveforms is a full 256 byte full page of memory, and we've got them aligned to an even page. So we have this particular version of the code has 5 different wave tables in it. There's the pure sine wave, there's the sine wave, which is an organ, and I'll show what that looks like in a little bit, as well as all these. Then there's the square wave, the sawtooth wave, and then the triangle wave. So this is where we have our lookup tables for our waveforms. Okay, so getting back up into the code section, and I'm not going to get into this too deep. The reason why is because the code is pretty compact. Simon did an outstanding job of optimizing this. There's a lot of self-modifying code in here as well. You can follow it along if you look at it closely. So the first bit here is the getting the note duration byte. So this is where we actually reference our song data. We look up our first value and we basically load that into our mdir, which is a single byte that we use to reference how long that note should be played for. The next section is our note sequencer, and basically what this does is it takes all the note data in that FCB statement for the 4 voices and places that into our temporary values for our sequencer. And then the next section is the music playback, and this is where everything really happens. And this is basically taking all the note data, combines it with the wave table values, the note lookup table, and basically sequences through the notes. So each one of these sections here is representative of each voice, and then down below is where we add everything together with our lookups into our wave tables. The final sum is then sent to our I/O port, which is E030, to be output to the sound card. Then down below, what we do is we check to see if we've finally reached the end of our tempo. If not, then we go back and we continue to cycle through the algorithm. And then we also will check to see if the note duration is at the end as well, and at which point, if not, we cycle back up. And then at that point, we're done with that particular algorithm for playback. So one thing I wanted to mention while we're in this section is this algorithm is tightly tied to two things. One, the speed of the system that it's being played back on. And in this particular case, I'm running my 6809 system at 2 megahertz. And then the other thing that it's tightly coupled to is the cycle time for this particular playback algorithm. And what I can do is show you the cycle count for this particular algorithm, and what we want to look at is this particular number right here, this 105. So what I'm doing is I'm just basically, as I assembled this code, taking a look at our cycle count, and for this particular loop from mplay 1 down to this branch here, it's 105 cycles. And what that is significant for is determining what kind of actual playback rate we can get, or sample rate that we can get with this. So if we take our 2 megahertz system, giving us effectively 2 million cycles per second, and divide that by our 105 cycles for this particular loop duration, that gives us effectively a sample rate of about 19,000 samples per second. And that's significant because that tells us how often we're able to output our data to our data port. So taking the Nyquist-Shannon theorem, cutting that value in half, that would effectively give us about 9.5 kilohertz as our maximum frequency that we can output. And as I had shown earlier in our note table, we are basically only going up to D7, which is about 2.3 kilohertz. So we're well within that spec. The other thing too we want to keep in mind is we definitely don't want to go up that high in frequency because what happens is we've only got 64 levels of output voltage. So those are pretty steep steps, and we want to maintain a pretty smooth curve as we're outputting this data. So if we were to try to put out frequencies that high, what's going to end up happening is they're going to get quite jagged, and they're going to sound, they're not going to sound very appealing. So one other thing I did want to mention, having a sample rate this high does have an advantage. And that advantage, not so much with the SWTPC, but for a system like the TRS-80 color computer, where you can actually have it as an IRQ-driven background player, what you can effectively do is take half of what you have left over for those cycles and apply that towards other code. So you could actually use this as a very effective background player for games and that sort of thing. So that's definitely one advantage to having this code extremely tight and optimized, where we're reducing the cycle count as much as possible. So that wraps up the code section. So now let's go have a listen to see what this thing actually sounds like. So while it's certainly possible to take and manually transcode note data and note durations from sheet music and convert that to the assembly code format, I came up with a little bit different approach when Simon and I were working on the 4-voice player with this utility called Coco Notes. And basically what it allows you to do is take various forms of music and transcribe those notes into FCB statements, data statements that you can use with the assembly code. So when I first started working on this, it occurred to me that I could write a parser for MIDI files, but then I realized that there were several different files out there that we could possibly transcode or transcribe. So came across this utility called OpenMPT, which stands for Open Mod Plug Tracker. And what this allows you to do, it sequences songs, and it allows you to take various types of music, drag and drop them into the OpenMPT utility, and it'll give you a consistent output that you can use with Coco Notes. So as an example, we have this Lemmings MIDI file here. So I can just drag and drop that in. As you can see, it gives us all our MIDI channels. We can select patterns, and you can see we have all our note and duration data here, and it looks like 6 different MIDI channels. So what I can do is I can grab all these patterns, and we just hit copy patterns, come into the Coco Notes utility, hit paste, and there's all our note data. It's text-based format. We can come in and we can edit this if we want to, if you want to do manually or make adjustments on the fly. But once you have this dragged in here, it automatically selects the first 4 tracks for us. And remember, we're doing 4 voice play back, so even though there's multiple tracks in here, there's 6 of them, we can only do a maximum of 4 here. So what we can do is we can adjust note values and note lengths, do voice adjust, pick waveforms and that sort of thing, but we'll leave it as is just to see what it sounds like. So we hit transcribe. The other thing that I did is, so after we hit transcribe, it shows us our note output. But the other thing that I did is, so it made it easier to be able to test and make adjustments more on the fly, more efficiently. I partnered this with VCC, which is a color computer emulator. So what I can do is I can just hit this play button, and it's going to come up off screen. But there's the emulator playing our song. And it's a little fast, so what we can do is we can make adjustments here. Let's bump that up to maybe 20 or so. We'll actually... And we'll try that, see what that sounds like. It's a little better. The other thing we can do is we can come in and we can adjust our voices. So we can pick different waveform for each voice. So we'll leave first one square, we'll do sine for the second one, and we'll do try Sawtooth for the last 2. We don't have to hit transcribe again because all we're doing is adjusting the note patterns, the waveforms, so we can hit play again. And there we go. So it's literally that easy to be able to create content that you download off the internet. I will make one note, though, in that typically a lot of MIDI files, a lot of XM files, a lot of the more complicated files use a lot of samples, and obviously those aren't going to transcribe very well at all. This does well with very simple songs, songs that are sawtooth or piano or organ in nature, but you can play around with it and get different effects. So the only other thing I want to mention too is I just recently added this Create S19 button here, which outputs an S19 file that we can use with the Southwest Technical Products system, as you've already seen. So another tool that I put together to improve on the 4-voice music player is this Waveform Generator. I was looking for a way that we could create waveforms that we would be able to import into the assembly code without having to do a lot of manual trial and error and manual calculations. So this utility is based on this app, this online app that I had found over at meettechnic.info, and it's based on additive synthesis, where you can adjust the frequency and phase and amplitudes of the various harmonics to create complex waveforms. So the utility outputs an FCB standard data for the assembly code that we can just drag and drop into our code. And what we can do is we can select how many samples we want, or what the sample count is in our particular waveform, and we can also pick what we want for our max table value. And right now we've got it set to 63. We're using a 4-voice player, so we want 0 to 63 for our maximum waveform values, because what we don't want to do is overflow that byte where we're going to produce odd harmonics. We definitely don't want to do that. So that's why that's in there. So the other thing that I did is created some presets, and these presets, a few of these ended up as the waveforms that we're using in the 4-voice player. So I'm going to go ahead and select a few of these and show you what they look like as well as what they sound like. Now the output that you're going to be hearing isn't from the utility itself. It's actually from the Southwest system, and you're seeing the waveform on the oscilloscope as I'm going through these. So one thing I do want to warn you is these can be a bit harsh. They're kind of loud, so you might want to turn your volume down. So the first thing that we're going to take a look at here is the sine wave, and the sine wave is pretty basic. Okay, so the sine wave isn't really that great for music. What we want to do is create more complex waveforms where we actually have harmonics. So the sine wave that we're using, or I should say the sine-like wave that we're actually using in the 4-voice player, is more of an organ sine wave. And you can hear what that sounds like with this preset here. A different one that we use in our 4-voice player is the square wave. The square wave, it's not your traditional square wave where you have on-off. You do have some harmonics in there. It gives it a more pleasant tone, a more ringing tone. This one's going to be extremely loud, so make sure your volume's turned down. Another popular one is the Sawtooth. This is one of Simon's favorite. It's got a real gritty sound, and it adds a lot of character to your music. And the last one that we use in our 4-voice player is the triangle wave. Triangle wave is going to be kind of soft. You use this for some subtle undertones, some percussion or whatnot in your music. And again, this utility made it really easy to be able to import these waveforms into our player without having to do a lot of manual work. And it's fun to just play around with to see what kind of different sounds you can make and what the effects are in the music. Okay, so for this last demo here, I've got the system set up again where we're going to send an audio file over the serial link to the Southwest system. The initial playback is going to be heard through the speaker that we still have mounted in the system, and that's connected directly off the soundboard. But I also have my stereo in here, and I've got over on this tripod here my microphone set up. So I'm going to record audio coming off the speaker system, and we'll have that kind of backfill. The other thing I wanted to show you real quick is I've got my PCB layout up on the big display there, and I'm hoping those are going to be in within the next couple days, and hopefully they work out well. All right, so I'm going to get this set up, and we'll be right back. So to send the file over to the Southwest system, we bring up our connection and send text binary file, and we're going to do star pause. It's a good sounding selection here. The load command is embedded in the S19 file, so it automatically initiates that when I start sending the file. This is going over 9600 baud, so it goes fairly quick. It's only a few K of a file. It's not very big either. Okay, so it's all set. One other thing I'm going to change, I currently have this assembled for the color computer, and what I'm going to do, which is set at 1 megahertz. So what I'm going to do is change the tempo, and to do that, the tempo value is located at memory location 0 E36. 36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E36. So we can go in and change that memory location. 0 E we can type. And we're going to change that to 2C. And again, to start playback, we need to change the program counter. And we go to 0E00, and then we hit go. And we'll bring in the amplified sound. Okay, so not too bad. So what I'm going to do to close out the video is I've got a few different songs that I've assembled for the Southwest system, and I'm going to play a few seconds of each and put those all together. If you want to listen to the whole selection, what I'll probably do is create a separate video that has the songs in their entirety, so you can go over there and listen to those. So that about wraps it up for now. Thanks. So not half bad, especially considering that we're only working with a 6-bit DAC and we're doing this with hardware that's almost 45 years old. I've been real happy with the progress on this so far, and I'm looking forward to continuing with the project. And speaking of continuing with the project, I was getting ready to wrap up this video, and what shows up today in the mail? I got my prototype boards from PCBWay. So obviously we're out of time for this video. We'll save this one probably for the next one. And I had to order a minimum of 5 of these boards. So if this works, I'll have a few available in case anybody's interested. At the very least, I plan on making all the software that I've created, as well as the assembly code for the songs and the Gerber files, KiCad files for these available as well on GitHub or something at the very least, so I can share and people can play with the tools and the boards if they so desire. But anyways, that's it for this one. Had a lot of fun and looking forward to the next one. Take care. Bye.